This is a talk about geometry and arithmetic of Calabi-Yau manifolds. So, as Rajesh mentioned, Calabi-Yau manifolds are of interest to physicists. They arise in string theory. You want to go in string theory from the 10-dimensional world to the 4-dimensional world that we see for reasons to do with constructing a theory that looks realistic in 4 dimensions. You want that process of going from 10 to 4 to be supersymmetric, and this leads you to Calabi-Yau manifolds. I'll say a little bit about what they are as we go on. It turns out, however, that there are at least 2 groups of people who think that they own. Let me say, in this process of going from 10 dimensions to 4, you have to allow for the fact that the Calabi-Yau manifolds depend on parameters. There are certain numbers that describe the size and the shape of the parameters and, of the manifold, and that's important in the physics. So our picture is that the world we see is 4-dimensional, but really attached to each point is a Calabi-Yau manifold that's very small, but although it's very small, it's not forgotten. And its topology determines certain features of the physics that we would see in 4 dimensions, but more subtle quantities are determined by the size and the shape of the Calabi-Yau manifold, and these are the parameters. So there are parameters, and understanding the parameters is very important, understanding how the manifold varies with the parameter is very important. And the canonical way to describe this variation is through the periods, which is a big part of this talk. And it turns out that there are 2 groups of people who are interested in the periods of the manifolds. So one group are physicists, and then there's a totally different group who are the number theorists. So the question arises, why are both groups of people interested in the same quantities? And there's no really clear answer, except that these are good ways, the periods are good ways of describing the answer. But I want to show, as we go along, some areas of common interest and how, firstly, there are sort of close analogies between studying the manifolds over the complex numbers, as physicists do, and also studying the manifolds over the p-Adic numbers, as number theorists do. They're very close analogies, and also some things are visible in one formulation which are not visible in the other, and this is interesting. Okay, so before we go any further, I'll be reporting on lots of work which was done with Zenia de la Osa and Fernando Rodriguez Villegas, who are responsible for most of the things, most of the observations that I will make today. So, supersymmetry, to cut a sort of fairly long story short, supersymmetry requires that you to choose a Calabi-Yau manifold in your compactification of string theory, and a defining property of the Calabi-Yau manifold is that it should admit a holomorphic 3-form omega. So Calabi-Yau for us will be compact, complex, scalar, and 3-dimensional. So 3 complex dimensions. And so here it admits a 3-form omega, which is purely holomorphic in the indices. So you can divide the coordinates up into 3 holomorphic coordinates and 3 anti-holomorphic coordinates. And the statement is it depends just on the 3 holomorphic coordinates and does so moreover holomorphically. So these coefficients here are moreover holomorphic functions. So an example of a Calabi-Yau manifold is the famous Quintic. So this is perhaps the simplest thing you can write down. you consider in CP4 complex projective full space, you define a submanifold by giving an equation here, P of x and psi. So it's the sum of the fifth powers of the coordinate minus 5 times psi. Psi is a parameter times the product of the x's. So you take such a slice of the manifold, and this gives you a Calabi-Yau manifold, as we'll see. Okay. And there's a beautiful point that the holomorphic three form not only exists, but it can be constructed. So if someone were to rush into the room with a gun, see, and say, build for me a holomorphic three form. So we have a space, we start in P4, say, build for me a holomorphic three form. You would say, well, what can you do? You have the coordinates, xa, you have the coordinate differentials, dxa, you have 5 coordinates in P4, so you have the alternating symbol. What can you do? Well, you could build something new. I don't want to use it. Epsilon A, B, C, D, E, xa. Why do you do that? Well, what else can you do? You have 5 coordinates in P4. One of them is always 1, so to speak. So you can't take a product of 5 dx's because one of the dx's would be 0. The epsilon is alternating, so you can't have epsilon xx because this would be symmetric, this would be antisymmetric, it would be 0. So all you can do is have 1x and 4 dx's. But now we were supposed to write down a holomorphic 3 form, and we failed in 2 ways. First of all, we've written down a 4 form. And it's not even a form defined on the manifold because since you're in projective full space, you can always make a scaling, replace x by lambda x, and this object, let's call it sigma. Sigma of lambda x is lambda to the 5th. Sigma of x. So it's not even defined on the space, it's defined in some bundle over the space. But sometimes to fail twice is pretty good, right? Because what we can do now is we take sigma, we're going to call the equation of the slice P so we have a space, P4, we have a slice in the space defined by the equation P equals 0. We take sigma, we divide by P, and now, of course, P of lambda x is also lambda to the 5th P of x. So we have something which at least is defined on the space, because the lambda to the 5th on the top line cancels the lambda to the 5th on the bottom line. However, it has a pole where P equals 0. So, but that's not so bad. So now we take this object, sigma over P, we integrate out one of the coordinates, we have something which pretty obviously by construction is holomorphic. So if you do this construction, pick a point on the manifold, integrate this 4 form around, then you end up with something which is invariant under scale and is in fact a holomorphic 3 form, and it all works because P was quintic. Right? So this is in fact why you choose a quintic in P4. And although this seems very special, you could adapt this construction many, many ways to construct many, many Calabi-Yau manifolds. in this way. So here's a holomorphic 3 form, and as I say, you get an expression. If you integrate out one of the coordinates, say xe, then you just get a residue integral, and this is the residue. So we'll come back to this in a bit. So in this example where we have the quintic, then the manifold depends on parameters. There are parameters built into the equation. There's this parameter psi that we wrote down on the board. But there's also built out of the space of bits holomorphic 3 form. If it exists, it's a one-line proof to show that if a holomorphic 3 form exists, it's unique. So it's unique up to a scale. And so this 3 form defines a line in the third homology. And the homology is a big space. We can think of the third homology defined over the integers. So that has a topological basis. So we have a big space. We have a basis. The basis is defined over the integers, so it doesn't vary with the parameters. And within that space, we have a line which, as we vary the parameter, this line moves around. And so the natural thing to do is to put coordinates onto this line, and we do that, if you like. One way of thinking of how you might do that is you choose a basis of cycles in here, basis of homology cycles called gamma, and you consider the integrals of omega over these 3 cycles gamma. And that gives you pi gamma, these are the periods. So these are the functions that we want to think about. One more point before we go on, something we could bring up later, but we can bring it up now. So suppose you have a 1-parameter family, to make things simple, 1-parameter family of manifolds such as the mirror quintic. I won't go into, mirror symmetry is a pretty story, but it's not particularly relevant to what we're going to do today. But if we take the mirror quintic, that will give you a 1-parameter family, which you can think of as being given by this polynomial. 1-parameter family of Calabi-Yau manifolds. And the Hodge numbers for this 1-parameter family is 8. Oh, sorry, let's go back. H21 here is 1. So B3, the third Betti number, you can have a 3-0 form. You can have a 1-to-1 form, its complex conjugate, or the complex conjugate of the 3-0 form. And so B3, the third Betti number, is 4. Now, I have an omega, and the manifold depends on parameters. So implicitly, this omega depends on parameters. This is this line that moves around in the homology space. So I can imagine differentiating with respect to the parameter, and so I can consider the quantities omega, the derivative, the second derivative, the third derivative, the fourth derivative. By now, I've got 5 quantities, but B3 is 4, so Betti tells me that there's a linear relation between these 5 quantities. And a linear relation between an object and its derivatives is a differential equation. So the omega satisfies a differential equation in cohomology. And when we integrate omega over fixed bases, the periods, the integrals of omega over the bases, are going to satisfy the same equation. So a fact that we put in the freezer is that these periods are going to satisfy differential equations. Okay, so I said we should all get one thing out of the afternoon, and so if you haven't seen it before, this is the one thing that you get out of the afternoon. And as if there are mathematicians in the room, I generally enjoy abusing them at this point, and I say that even a mathematician should know how to integrate. So we're going to compute a period. Okay. So we're going to compute it. Can I use this on the board? I can. It's wonderful. Right. So we're going to compute it for the quintic given by this equation. Okay. The omega is invariant up, is defined up to scale, so I put in a scale minus 5 psi here. Here is x1, dx2, dx3, dx4, dx over dp, dx5. This is our one form. This is our invariant 3 form here. And we're going to choose as our cycle 3 small circles around x2, x3, x4 is naught. So we look at the x2, x3, x4 is naught cycles. We set, since we're in projective space, we set x5 to a constant. No, we set x1 to a constant. So x1 is a constant. It could be 1, but it's better to leave it as a general thing. x1 is constant. We have small circles going around x2, x3, x4, and we have a quintic equation, and we solve the quintic to get x5. And we specify the root by saying that we want the root that's small as psi goes to infinity. So you can check the roots of this equation, and as psi becomes large, you can check that one of the roots becomes small and the other 4 become large. So we're going to choose the one that becomes small. Okay. So the first step is easy. We said that we got the holomorphic 3 form by integrating a 4 form around a loop. So we undo that process. Okay. So we got this form by integrating out over x5. So let's just back up one step. So now we put in gamma 2, gamma 3, gamma 4, gamma 5, a small circle around x5 equals 0. We put in the integral here and the 1 over 2 pi I. And so we've backed up from here. We could go from here back to here by integrating out over x5. Everybody happy? Good. Now, the next step requires staring at this for quite a while. That is obvious. This integral here looks as if it depends on x1. Is anyone willing to admit to thinking that it depends on x1? Yes? Well, you might think it depends on x1, but it doesn't, because everything was set up so that you could scale the coordinates. This integral and this one before it are invariant if you scale the coordinates by a constant. Okay. So whatever x1 is, I can always scale it to 1 without changing the integral. So the integral doesn't depend on x1. Since it doesn't depend on x1, I can smuggle in 1 is integral dx1 over 1 over 2 pi I. 1 over 2 pi I, integral dx1 is 1. I can smuggle this in under the integral sign. So we smuggle it in under the integral sign, and we cancel the x1 here. So here's the dx1, an extra 2 pi I here. So now we have 5 integrals over 5 circles. So this method is sort of, if you can't do 3 integrals, perhaps you can do 5. This is the sort of thing. This is sort of philosophy. Now you rewrite, the bottom line is p. It's the sum of the 5th powers minus 5 psi, the product of all of them. You pull the product outside. We had put in a minus 5 psi in at the beginning, which cancels the minus 5 psi inside here. And so now this times this gives us p. So this is the integral. And this you do by expanding this out in a series. So you expand it out like this. And here, this bit, with much pleasure, you realize this integral you can do. So integral dz over z to the m is 1 over a small cycle is 1 if m equals 1 and 0 otherwise. Okay, so we know that. And so this integral we can do, we expand up. If there's any power here that's not 0, the only term in here that contributes is the constant term. Any other power in there will give 0 by this rule. Okay? So now we have to pick out the powers, the constant term in this. So you have to cancel. On the bottom line, you have x1 to the m, x2 to the m, x3 to the m, so on. On the top line, you have something else. You have to have equal powers on the top and the bottom for the powers to cancel. So this can only happen if m is a multiple of 5. So if m is a multiple of 5, say m is 5n, then you can distribute n to each of these terms, and you get 5n on the bottom line, and so then you can pick out a constant term, and the multinomial theorem gives you that the constant term, so what you want is x1 to the 5n, x2 to the 5n, x5 to the 5n, over x1 to x5 to the 5n, and that's associated with a 5n factorial over n factorial. So in this way, you get this function. Okay, so we've done our first period integral. Okay, so we've got a pi of lambda. So lambda is convenient just to write lambda as 1 over 5 psi to the 5th. We've got a pi of lambda, which is this function. And this satisfies a different, we said it would satisfy a differential equation. It does satisfy a differential equation. Here's the differential equation. It's a fourth order differential equation. Theta is lambda dd lambda. And if you just check it, then this satisfies the equation. Now it turns out that this is the one period that's easy to satisfy. There are in fact 4 periods. It's the one period that's easy to evaluate by integration. But since we have a differential equation with 4 roots, with 4 solutions, it's reasonable to think that the other 3 solutions are the other 3 periods. And in fact, that's the assumption that we make. You want to check, if you're presented with an equation like this, then the first thing you do is check the indices. So you look for a solution, you have a L of pi is 0, you try, lambda equals 0 is the singular point, you try, pi goes like lambda to the epsilon, you discover that epsilon to the 4th. This tells you that you're dealing with logarithms, that the solutions are a series, there's a logarithm times a series, a log squared and a log cubed. And more precisely, I have to tell you what these solutions look like because we'll be making reference to them in a minute. So the first solution is the one we've already found, so this is just another name for it, this is a series. The second solution is the first solution times log lambda plus another series. Then there's another solution, which is f0 times log squared lambda, 2f1, same f1 as this, log lambda plus f2 of lambda, then finally a pi 3 f0 log cubed plus 3f1 log squared plus 3f2 log lambda plus a new solution f3. And the way you find these solutions is by using the method of Frobenius. So you recall from when you learned about differential equations that you try a solution like this to the differential equation, and you differentiate with respect to epsilon. What you're actually doing is solving, you find a recurrence relation for the coefficients. What you're actually doing is solving this equation here, and you can see that If you set epsilon is 0, you get a solution. If you differentiate with respect to epsilon and set epsilon is 0, you get another one, and so on. And in this way, you generate 4 solutions. Lambda is that, so we have a parameter, so I've carefully rubbed off the equation. So we had an equation which sigma xi is 5 xi is 0, and then it turns out to just be. So the equation depends on psi, but it turns out to be easier to make reference to lambda with just a rewriting of psi. So thank you for that. Okay, so that's the periods. So you can actually integrate and find a period. You can find from the integral, you can find a differential equation, and the other periods satisfy the same differential equation. And by and large, this gives a practical way of evaluating periods. But now ask a very sort of strange question, at least one that's very strange to a physicist, which is look at this equation again, and now think of the x's as defined, say, over a finite field. So think of the x's defined over Fp, and ask how many solutions are there, and think of, let psi be an integer, and then it makes sense to reduce everything mod p, and ask how many solutions are there to the equation mod p. So this will give you some definite number. You can write a little code in Mathematica where actually there are p to the 5th points. You go through, check each one, see if it satisfied the equation. And that number you'd expect to jump about in a strange way depending on p and the parameter and so on. The strange thing is that the number of solutions is calculable, and this is related, and the answer is related to the period. I guess I won't explain what a finite. Should I explain what a finite field is? Okay, a finite field, if you're dyed-in-the-wool physicist, then this is field theory for physicists, right? So, a finite field is a set on which you can define addition and multiplication, and they have the usual associative and distributive properties. So you can talk about adding and multiplying, and addition and multiplication. So F is an abelian group with respect to plus, which means that also the fact that this is a group means that minus is defined. So the group operation is plus, and therefore there's an inverse operation minus, and you don't expect the 0 to have such a group has a neutral element, which is called 0, and you don't expect 0 to have a multiplicative inverse, but the rest of the field has an inverse for every element. So F star, which is, F star, which is F minus 0, has to be an abelian group with respect to times, which means also that you're allowed to divide. So there's an inverse of every element. And then there's one of these amazing facts that finite, so a field can be either finite or infinite. Infinite fields are the usual things. The real numbers are a field. The complex numbers are a field. The integers are not a field because the inverse of an integer is not an integer, right? But you can have a finite field, and if a field is finite, then the number of elements is p to the k for some p and k. So it's a prime power for some prime. Okay. Here's what must be almost, sorry, I don't have the hang of this. What must be almost the simplest field, so the field with 7 elements. So if you think of this you can think of this as the integers mod 7, and think of x to the minus 1, so think of f star, you drop the 0, and then indeed every element has an inverse. So 1 times 1 is 1, but 2 times 4 is 1, mod 7. So 4 is the inverse of 2, 5 is the inverse of 3, then it goes on, 6 is the inverse of itself. So F7 of the field of numbers, of integers mod 7 is a field. And then there's an old result that goes back to Fermat, which says that a to the p is a mod p. Right? So this is very easy to prove by induction on A. And you can take a to the p minus a, and if you don't believe induction on A, then what's it? As I like to say, 3 to the 5th is 243, right? And 243 is indeed 3 mod 5. So if you consider that a proof, then that's okay. Okay, if you take a to the p minus a is 0, and rewrite it this way, it follows that a to the p minus 1 is 1 if a is not 0, and it's 0 if a is 0. So mod p, you take an integer, raise it to the power p minus 1, that number is 1. If the number was non-zero, that number is 1 mod p. This is at the basis of most primality testing routines. This is, I mean, this wouldn't be true if p were not prime. At least in general, it's not true if p is not prime, but it is true if p is prime. And there's another elementary fact that's very useful if you want to know, if you want to sum A over the field, and you consider the sum of a power of the field element, then this is the same thing as BA to the n, where B is any field element, you pull the B to the n outside. B to the n is, this has to be true for any B, and this forces the sum of the ANs to be 0, unless B to the n is 1, and B to the n is 1 if n is a multiple of P minus 1. So you get a rule that says that the sum of A to the n over a field is 0 unless n is a multiple of P minus 1, and if P minus 1 does not divide n, the sum is 0. If P minus 1 does divide n, then you have 0, which gives you 0, and every other element will give you 1, and there are P minus 1 of those, so that's minus 1. So you get a simple rule for adding up sigma A to the n. Okay, so now we have to do this, and Xenia taught me this the first time. So this is very good, right? If you want to count the number mod p, so there's a definite number. If you want to count this number, the number of solutions of p of x of size 0, right, then there's a way to do it. So we want the number exactly, but for the moment, let's conform ourselves with counting mod p. That's relatively easy. You take this number 1 minus p to the, this is the defining equation, to the power p minus 1. Right? And you can see that gives you the right number mod p, because either x satisfies the equation or it doesn't. So if it does satisfy the equation, then big P is 0, and then you add 1 to the running total, and that's good. And if x does not satisfy the equation, then this is not 0. You raise it to the power p minus 1, which is 1 mod p. 1 minus 1 is 0 mod p, so you add 0 to the running total, and that's right. Okay, so this gives you the number mod p. Okay, then you get the real surprise, okay, which Xenia also told me, I think, that if you do this calculation, which is easy, right? You have many sums to do, but the innermost sum you can always do because you have sums of powers of x's over the field, and you know how to do that by what we said on the previous slide. So if you do this, it's a side of paper, you'll find that the number of solutions, number of points mod p is this, is to take the fundamental period you take the first p over 5 terms, and that gives you the answer. Mod p. Okay? So out of nowhere, the periods have arisen. Now, you want to do more, you can expand this number. You want it exactly. You can expand it as a 0, as the number mod p. This is the number we've just talked about. Plus, you can expand it in base p. So you can write it as plus nu1 times p, plus nu2 times p squared, up to nu to the 4th times p to the 4th. If you get there, you're done, right? There are less than p to the 5th points. So if you can find these coefficients, you're done with calculating the number of points. And this leads rapidly into p-Adic analysis. What you really want to do is look at this as if you were doing this by a successive approximation. You want a scheme for considering p to be small. So you evaluate the first term, and then you want to evaluate the second term by perturbation theory, and so on. And there's a way in which you can do that, which leads rapidly into p-Adic analysis, which I won't go into, but there's a consistent way of considering p to be small and evaluating this by perturbation. And by now, we've probably forgotten what we said were the periods, but let's write it up again. So we said that there was a period, pi naught is f naught. There was another one, pi 1 is f1 log lambda. f0 log lambda plus f1. Pi 2 is f0 log squared lambda plus 2f1 log lambda. f2 and pi 3, I won't write it all down, log cubed lambda. And if you carry on, what you find, and the first result isn't really right, it's simplified a bit. So let's deal with the case that 5 does not divide p minus 1. That's easier. There are lots of times in which 5 doesn't divide p minus 1. And then what you find is this number is you take the fundamental period to p terms, you add p over 1 minus p times f1 primed plus 1 over 2 factorial f2 double prime squared f2 double prime plus 1 over 3 factorial 1 minus p cubed. You're beginning to see a pattern here. But it's not quite that. So I didn't say, we could have said, asked if this basis was unique. So when we write a basis of solutions to the differential equation like this, is it unique? It becomes unique if we say that f0 of 0 is 1, which it is, and fj of 0 is 0 for j bigger than 1. So let's make the basis unique by doing that. And then you find that there's a sort of something that you think is a fly in the ointment. So, and this becomes plus 3, 1 over 3 factorial, p over 1 minus p cubed, f0, 1, 2, 3, and then the next term would be 1 over 4 factorial, p over 1 minus p to the 4th, f4, 1, 2, 3, 4, and so on. Oh, okay, so that's a good question. That's an excellent question. And let's just say what prime is. Prime is theta. So theta is this lambda d du lambda. Yeah, so it's good, right? We said the following. We said that nu is nu naught plus nu 1p plus nu 2p squared plus nu 3q plus nu 4. Now it turns out that the answer is pretty close to p cubed. So actually, if you know the integers up to nu 3, you're done. Okay, you can work out the 4. But we took this to Roger Heath Brown in Oxford, and we said, isn't this a pretty formula? Expecting praise. And he said, no, your formula is very ugly. Right? And he was right, because what we had was a formula like this. Or perhaps we, right? And the thing is, you want a number like this. We were giving an answer which went on, plus nu 5, p to the 5th, plus, and then you were saying, well, we know that only this bit is what you need. Okay, so you do the calculation and then you stop. And the first 4 terms are what you want. And much nicer is to give a calculation where the thing naturally stops and all the higher terms are 0. Okay? And so what you have to do that is take the order p to the 4th and add dot, 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 where the series continues in the way that you expect. Now, what does that mean? All these came from writing down as a solution sigma a n of epsilon lambda to the n plus epsilon. And if you take this function and its first 3 derivatives, you get solutions of the equation. If you just keep on differentiating, you forget that epsilon to the 4th is 0. Right? You just forget about that, and you just keep on differentiating. Then you'll generate here more solutions with an F4 and F5 and so on. Those are precisely what you want to put into these. Right? So this looks like things that crop up in physics, where you have these ring relations. You simply forget about epsilon to the 4th is 0. Right now, quantum corrected things. I don't want to go into that. Oh, so this is a change of basis. Right? So somewhere this is telling me I'm in the wrong basis, that I need an F3 twiddle, which is F3 plus a certain number plus F0 basically. And in fact, I need an F4 twiddle, which is F4 plus F1. Okay, so there's a change of basis in the. I could get rid of this second term by making a change of basis, redefining F3 by a multiple of F0. Yeah. Oh, because it says so. Yes. Plus this. Okay. And I could get rid of it, but I don't want to get rid of it. Well, let me just say why you don't want to get rid of it. So something pretty happens. So this is a story. So there's something here that's pretty, right? I mean, there's something pretty. We set out to count points. And we're counting points by solving differential equations, which of course, I mean, to me, at the beginning, that was a surprise, right? That you can count these points by solving differential equations. So that's an interesting thing. There's another thing that comes up. If you think about this problem over the complex numbers, then there's a God-given basis. It's not unique, it's almost unique. There's a basis, I have to hurry up. There's a basis of periods which are the integral periods given over integral cycles. So these, in special geometry, we won't go into this. These are the GAs, ZBs. So there's a set of periods that you get by choosing a basis of integral cycles. There's the basis that we've chosen here. The two are related. So there's a matrix of constants that relates the integral basis to this basis. Here you have constants. You get a matrix. If you look, you can compute the matrix. I won't do it. You can compute the matrix. The entries of the matrix are rational numbers extended by zeta of 3 over 2 pi I q. So when you do these computations, there's a 3-loop term which changes things in the expansion of the prepotential. Right, so you need to know the prepotential here. There's a 3-loop term which comes when you expand this, and the coefficient of that term has a zeta of 3. And so, and you get a so there's contribution. So the statement is that the coefficients in this matrix are rational numbers, except that some of the numbers involve zeta of 3 and 2 pi I cubed. So the rational numbers extended by that, and it comes multiplied by the Euler number, which means that if the Euler number of the manifold is 0, then these are in fact just rational. This number here is chi zeta p of 3 over u car. You're doing p-Adic analysis. You have all the processes of analysis. You have p-Adic special functions. Zeta p of 3 has a meaning. This twist in the basis is some sort of very nice analog of this. You get here the p-Adic zeta function. Okay, let me hurry. Okay, so let's get on to this. We've got a way now of calculating the numbers of points. In fact, we calculated the number of points over FP. We could have calculated the number of points by an extension. We could have calculated the number of points over the field with p to the k elements for each k. Well, at least for the first few values of k. Let's call the number of points over fp to the k, let's call it nk. It depends implicitly on the parameter. Or I'm calling it r in the slide. So let's do that. Okay. Mathematicians like to write down a generating function. That's the one that's there. Okay. Given these n's, you calculate this generating function like this, and the Weil conjectures tell you that this is a rational function. Sorry, I'm confused about that. And what you find is that this function here is a rational function like this. The interesting bits are the bits on the top line, is a polynomial of, is quartic in this counting parameter t. You get a quartic, this coefficient here is the same as this one. it depends just on two coefficients, A and B. So in fact, it's enough to know N1 and N2 to determine the zeta function. And these numbers, so you would pick up psi and you would compute these numbers, and these numbers depend on psi. A and B depend on psi. And this is the answer if the manifold is smooth. Right? So you get an answer, you can make tables of A and B. Suppose now that the manifold is singular, so you have a conifold, you choose a value of the parameter such that the manifold becomes singular, and that quartic, the interesting quartic factor degenerates. First of all, it becomes cubic, and then it factorizes, so you get 1 plus or minus pt, 1 minus alpha pt plus pq. Okay. This plus or minus turns out to be just depend on whether p is a square mod 5 or 5 is a square mod p. So that's a fairly straightforward factor. And then this is the pth coefficient of a modular form of weight 4 for gamma 0, 25. So there's a modular form for gamma 0 of 25 means, gamma 0 of n means you look at different A, B, C, and D, right? You look at A, B, C, D in SL2Z, and gamma 0 of n corresponds to the case when n divides C. C is a multiple of n. Okay, such things form a group. So there's a modular form of weight 4 for this group. It has an expansion. You look at the Heath term in that expansion, and that gives you the number that occurs here. Modular form of weight 4. I guess it's a cusp form. Yes, cusp form. So here's something interesting, right? Out of nowhere, we've gone to the conifold, and out of nowhere has appeared gamma 0 of 25. So we've got a group from somewhere, from out of nowhere by studying the number theory. And the question is, what's the physics interpretation of this? Right? If you ask a number theorist, there are probably number theorists in the room, for which I apologize, if then I apologize, right? But if you ask a number theorist why this happens, they say that's number theory. Right? There's no real understanding of why this, or the answers get very complicated. Right? We have a much more detailed view of these things if we think of string vacua, a much more detailed view of what a singular manifold is. Perhaps we can say what's going on. I mean, we have a view of brains shrinking to 0 or something. Perhaps we can say how these groups appear. Okay? And if you allow me just 2 minutes, this goes very deep. This goes very deep. It's very like what happens with elliptic curves. Right? If you have an elliptic curve, elliptic curve like that, which is a poor man's Calabi-Yau manifold, so Calabi-Yau one-fold, right? You compute the zeta function. It has more or less the same form. 1 minus alpha pt plus pt squared. The weights are a bit different. 1 minus t, 1 minus pt. If you say what Wiles did, so Wiles and his collaborators, they did it slightly out of order. But the proof of the Fermat conjecture was to prove that every elliptic curve is modular, which means that every elliptic curve has a zeta function of this form, and the alpha that occurs here is the coefficient of a modular form of weight 2. Okay. That was the hard part. That was the 200 pages of inscrutable mathematics, was to prove that statement. Once you have that statement, you consider the Frey curve. So you write down this elliptic curve. First thing to note, suppose there's a counterexample to the Fermat conjecture, then it's sufficient actually to have a counterexample for prime power, a to the p plus b to the p is c to the p. Because if you have a to the n plus b to the n is c to the n, n is either prime or it's not. If it's not prime, then you can extract a prime factor, so you can write n as p times k, and then you have a to the k to the p plus b to the k to the p c to the k to the p. So it's enough to study this. If there's a counterexample to Fermat, there's another counterexample with a, b, and c bigger, but the power smaller, and you can carry that on until the power is prime. So it's enough to know that it's enough to prove there's no counterexample to this. You consider the Frey curve, you can show that if a to the p plus b to the p is c to the p, you can show that this is not modular. That's relatively straightforward. So now you have it. Wiles and his collaborators have shown that every elliptic curve is modular, so there's no solution to this equation. So this sort of thing goes very deep. I still don't know what it is, but it's a challenge to us to try.
In the previous transparency, before it factorized, it went up till p to the 6th, didn't it?
Yes, it went up to p to the 6th, yeah.
So that's...
So that's this is the statement when the manifold is smooth.
Yes.
Okay. So there's probably some statement involving groups here, but the group is believed to be some subgroup of SP4, and much less is known. So there's a story here involving SP4 or subgroups, but much less is known about modular subgroups of SP4. Modular groups associated with SP4 and its subgroups, modular forms associated with SP4 and its subgroups. Right? However, if it becomes singular, then it becomes modular forms of subgroups of SL2, and much more is known. So you can look up all sorts of things in tables.
So, but is there a similar pattern for other Calabi-Yau?
Oh, sure. No. This is very general.
This, this sort of...
Yes, no, this is very general.
That if you go to other Calabi-Yaus and go to their singular point.
Yes, we made a story about periods and differential equations and zeta functions. And Dulko van Straten realized early on that you can go from a differential equation to a zeta function. And he has a list, he and Almquist have a list of 500 or so differential equations, all we believe, or they seem to be, all associated with one-parameter families of Calabi-Yau manifolds, and in the project that we're doing with Xenia and Dulko, at the moment, we're looking at this, And it all seems to go through for all the examples we've looked at, all have completely parallel.
The same alpha p?
No, the groups change. But what is true is that you have a one-parameter family, you have a factor of degree, which when the manifold is smooth, you have a zeta function factor, which is of degree 4. As soon as the space becomes singular, it goes down to a linear term times a quadratic term, and the quadratic term is related to a modular.
There are no further questions, so let's thank Philip again.